I'm going to tell you today about Celerion's highly automated ECG analysis and how this can be a key to better thorough QT data more cost effectively. My name is Bill Wheeler and I am the Therapeutic Area Lead in Cardiovascular for Celerion. The bottom line in your thorough QT study is that variability is a major determinant of sample size. As you can see from this graph, as the variability increases, the sample size increases markedly. This diagram is a typical study setup with a determination of drug change of approximately 3 milliseconds, alpha 0.05, and a 95% power. Looking at that, if the variability, within subject variability, is about 10 milliseconds, that's 45 subjects. You can see if you go down even to 7, it's about 22. So variability is a real key determinant in sample size. Now, to talk about how all this works, you have to talk about the ECG measurement modalities. Semi-automated is the standard process where the computer places the calipers, makes the initial measurements, and then every ECG is confirmed by a cardiologist. And this is the standard in abnormal ECGs, but probably not necessarily in normal ECGs. This is sometimes also called a manually adjudicated method. There's then, on the opposite stream, there's the fully automated, where it's machine read only, it's a black box. This can be consistent in normal ECG readings and may actually decrease variability. But there are reading characteristics that cause inaccurate measurements, and there are outliers that occur with this. Moxifloxacin, the usual positive control for most thorough QT studies, is one of those things that can cause abnormal ECGs. In a highly automated approach, what we do is have the computer algorithm measure all the ECGs, and those that have characteristics suggesting an accurate measurement are automatically put in the database, while those that have characteristics that could indicate that automated reading is not as accurate are then reviewed for cardiologists, and that's about 10% of the ECGs. So in some ways you can call this semi-automated on steroids. Now let's look at how we do this. There's 3 components that we've used from the AMP software to do this. The first is optimal ECG extraction. The second is the use of a representative complex that not only minimizes artifact, but also smooths heart rate beat-to-beat variability. And finally, targeted cardiologist review. Anteris is the program that does the optimal ECG extraction. With Anteris, a time window around each nominal time point is selected. Anteris then goes in and selects 10-second ECG strips based upon preceding stable heart rate and level of artifact. It's very important to have a preceding stable heart rate because the heart rate correction factors are inaccurate if the preceding heart rate is not stable. Here's an example. The strip at the top, you can see towards the middle, it looks like there's an increase in heart rate. And if you look at the graph down below, the fuchsia line shows that indeed the heart rate is increasing at that time. The RR is decreasing. The heart rate is increasing at that time. And so that would not be a good time to take an extraction. However, right up on the shoulder to the left, where the green arrow is, would be a good time to take extraction. I want you to note in the background that the actual beat-to-beat variability is still there. This is just an averaging. This shows how the program, even though the heart rate may have a stable preceding heart rate, there are times when the artifact needs to be eliminated. The strip on the left has a lot of artifact. The one on the right is a clean strip and much easier and more accurate to measure. So now let's talk about the representative complex. This is a standard 3-individual raw beat presentation used in many core labs. At the very top you can see the RR interval, which is the time between each QRS, and that goes from 748 to 820, and that's pretty much standard. Our heart rate varies as we breathe in and out. And the QTCF is that QT divided by the cube root of the RR interval. So for each and every one of these beats, there's a different correction for that QT. In addition, if you look down at the graph in the lower left, even though the fuchsia line is smooth because there's a stable heart rate, there's still beat-to-beat variability, as I mentioned above. If you look at the QT intervals that are listed, they go from 370 up to 354, and that's because of artifact. If you assume all of those are 370, which is probably most accurate, the one on the right is probably the most accurate measurement. If you assume all of the QTs are 370, based upon the variability in RR interval, the QTC varies from 395 to 407. So you get quite a bit of variability just based on the beat-to-beat RR interval. Representative beat, for each and every beat that is on each lead, are summed together and a median is taken from that. And this markedly minimizes the artifact. In addition, it takes into account some of that beat-to-beat variability, because rather than correcting each QT interval for the preceding RR interval, it's corrected by an average of those RR intervals, which smooths it out. Here's a standard 12-lead ECG with very difficult to see T waves. About the only one that's visible is in lead V2. Although the others have them, they're very difficult to see because they're low amplitude T's with lots of artifact. If you make a representative beat for each one of these leads, you'll see the T waves show up much better, as they do here. And as you can see now, there are good T waves visible in almost all 12 leads. So you don't end up throwing away data because you can't see the T wave. And it eliminates the variability that we saw in those 3 individual raw beats. So now let's go to the targeted cardiologist review. These graphs show a correlation between an automated algorithm and a manual reading. The top one is an older algorithm. If the algorithm and the cardiologist read exactly the same, all of those dots would go right along that horizontal 0 line. However, you can see in the older algorithm there's a lot of spread between the manual measurement and the automated measurement. And that's one of the things that's made people uncomfortable with more automated processes. However, as algorithms have evolved, in the bottom one you can see there's a much better correlation. Those dots are much closer to 0, but there's still significant outliers that are present. And if you could take and actually decrease it till it's within these 2 red lines, you could cut variability even more. And that's what we plan on doing. Here is an ECG that has actually been made abnormal by moxifloxacin. It has biphasic and inverted T waves, and this is the kind of ECG that's sometimes difficult for an automated algorithm to measure. This is a superimposition of a median beat from each of the 12 leads. The blue background are the measurement bars put down by the algorithm. The PR interval, the QRS, is the darker blue area, and from the beginning of the darker blue area to the end of the blue is where the computer read the QT interval. As you can see, many of the leads look like they do finish or do end right there where that blue area ends. However, we see that in actuality some of the leads go way beyond that, and a cardiologist would read that out here. So this allows the cardiologist to look at those ECGs that may have T-wave abnormalities that could be inaccurate and can be more accurately measured by a cardiologist than the current algorithm. So decreasing variability with the AMP software, we have optimal ECG extraction, representative complex, and targeted cardiologist review. All of these things come together in the 3 pillars that we have for our hybrid phase 1 ECG core lab, with using a Bluetooth Holter and the highly automated ECG processing. Thank you.